Let's look at example here, 2 here. It says using the product rule. So we do need to use the product rule. Even though we don't need to be able to solve it, the problem asks us to, so we are forced to use the product rule. We have a product here, the first function being 1 over x plus 1. 1 over x plus 1 is our first function. Our second function being 2x plus 1. So it's the product of 1 over x plus 1 times 2x plus 1. So what do? We look at the first, the derivative of the first. We look at the second and the derivative of the second. Let's give that a try. The first, when I look at the first, it's 1 over x plus 1. Now I need to find the derivative of the first, and if this is going to take you a little bit of time, that's perfectly fine. This is x to the negative 1 plus 1. So if I was finding the derivative of that, it would be negative 1x to the negative 2 plus 0. The derivative of a constant is 0. So really the second is, what would that be? Negative 1 over x squared would be the derivative of the first one. The second term was simply 2x plus 1. Well, what's the derivative of 2x plus 1? Well, that'd be 2 times 1, which is just 2. And then the derivative of 1 is 0. So the derivative would simply be 2. The derivative of 2x plus 1 is 2. What's the product rule say we do again? It says we do the first times the derivative of the second, plus we do the second times the derivative of the first. So y prime would equal 1 d2 plus 2 d1. In this case, 1 would be 1 over x plus 1 times the derivative of the second, which is 2, plus the second, which is 2x plus 1, times the derivative of the first, which was negative 1 over x squared. Let's go ahead and simplify this out if we can. Distributing that 2 through to both of those terms, I'd have 2 times 1 over x is 2 over x. 2 times 1 would be plus 2. Now let's distribute the negative 1 over x squared to both of those terms. 2x times negative 1 over x squared. Let's go ahead and let's not simplify yet. I want to make sure you see it. And then I'm going to do 1 times negative 1 over x squared, so that'd be minus 1 over x squared. So I do notice on this term, this turns into a 2 over x, because the x's simplify. And then if you notice, I have a 2 over x minus a 2 over x, so those two things are actually going to cancel now. So it looks to me like I'm left with 2 minus 1 over x squared. I'd be perfectly happy with this on the test. That's the final answer to me. I do want to let you know, though, if you get the wrong answer 3 times in your online homework system, it might show you a different answer. So what's that different answer that you're seeing? Most likely all they did was get a common denominator. So to get a common denominator, if we continued this problem, you'd have to multiply the first term by x squared over x squared. So it'd be 2x squared. When you combine it, it would end up being 2x squared minus 1 all over x squared. And that would be another version that you would probably see in the homework system. I am okay with you leaving it separate. I would have stopped this problem at 2 minus 1 over x squared. You would have gotten full credit for either of those answers, but again, I would have stopped early. So if you get something as a final answer, or if you get it wrong 3 times and it tells you the final answer and it looks weird, looks way different than what you have, it might be something as simple as that of them just getting a common denominator. Let's go on and look at example 3 here. It says find the derivative of each function. Well, here it doesn't say that I need to use the product rule, does it? And quite honestly, if it doesn't say I need to use the product rule, I'm not going to use the product rule. If it doesn't say to use the product rule, I'm not going to use the product rule. So what would I do on this one? I would have multiplied both of these terms times 3x. So I would have said y equals, 3x times 2x squared. 3 times 2 is 6, and x times x squared is x cubed. Remember, you add the exponents. Then we have 3x times 5x. 3 times 5 is 15. X times x is x squared. And that would tell me I could simply find y prime, the derivative. 6 times the derivative of x cubed would be 6 times 3x squared. 6 times 3x squared would be 18x squared. Plus 15 times the derivative of 2x. 15 times the derivative of x squared. The derivative of x squared is 2x, so that would give us 30x. There's my derivative right there if I just multiplied it out. Well, what would have it been if I had used the product rule? Our first function was 3x. Our derivative of our first function, well, the derivative of 3x is just 3 times 1, or 3. Our second function was 2x squared plus 5x. The derivative of the second function, well, the derivative of 2x squared is 2 times 2x, which is 4x. The derivative of 5x is 5 times 1, which is just 5. Again, you would do first times the derivative of the second, plus the second times the derivative of the first. So we would have had y prime equals 1d2 plus 2d1, which in this case would be 3x times 4x plus 5, plus the second, which was 2x squared plus 5x, times the derivative of the first, which is just 3. Multiplying out that 3 times the 3x times the 4x plus 5, 3x times 4x is 12x squared, 3x times 5 is 15x. Now we have to multiply that 3 through. It's 3 times 2x squared would be 6x squared, and 3 times 5x would be 15x. Combining like terms, we have a 12x squared plus a 6x squared. 12x squared plus 6x squared is 18x squared. 15x plus 15x is 30x. Notice we got the exact same thing for the derivative, regardless of which method we used. And since this problem didn't specifically state which method we used, I would have accepted either one of those in this case for this answer. Seeing that you distributed first, and then you took the derivative of each term. Probably could have shown an extra step in there, but that's okay. Didn't need it. Pretty straightforward derivative there. I can see what you did. Look at example B. What would you do with example B? Well, example B, you could see this as a product. You could see it as the first function being 3, but then notice the derivative of the first function is 0. The second function here is 2x squared plus 5x. So the derivative of the second function, let me go back. The derivative of the second function, 2 times the derivative of x squared, 2 times 2x is 4x. 5 times the derivative of x would be 5 times 1, which is just 5. So if I did 1d2 plus 2d1, 1d2 plus 2d1, in this case it would be 3 times 4x plus 5, plus 2x squared plus 5x, times the derivative of the first, which was just 0. Of course, 0 times anything is 0. So I'd do 3 times 4x plus 5 would be 3 times 4x is 12x, and 3 times 5 is 15. So my final answer should be 12x plus 15. Did I need to do that, though? And the answer is no. There's a bunch of different ways I could have done this problem. I could have also noticed that, look, 3 is just a constant, isn't it? And if 3 is a constant, isn't that a constant times a function? So shouldn't, let's do it a second way, shouldn't y prime be equal to 3 times, now I'm going to use some notation. You're going to see me use this throughout the semester. It's really not good notation. I put a prime on it, and what I mean is I still need to differentiate it. So really what I should be writing is d dx for the derivative with respect to x of this, but my lazy notation is just saying prime. I'm going to find the derivative of that. Because isn't the derivative of a constant times a function the constant times the derivative of the function? So this would be 3 times, well, what's the derivative of the inside? Well, again, the derivative of 2x squared would be 2 times 2x, which is 4x. Derivative of 5x would be 5 times 1, which is just 5. And this is how we're getting the 12x plus 15. So a second way of doing it, you only need to use the product rule if it tells you to use the product rule. Multiple different ways of doing these problems. I would have accepted any of these ways because it was not clearly written up in the problem that this is how you had to solve it. But I wanted to show you guys multiple ways of doing it to know that you can get answers in more than one way.